Hi everyone. Today we'll be going through another ionic equilibrium question. So this question is testing mainly on the titration curve. So let's take a look. Before we go into it, let us have a basic understanding of titration curves. So over here, 25 cm cube of 0.1 mole per dm cube of monobasic acid X is titrated with 25 cm cube of 0.2 mole per dm cube of NaOH. The endpoint cannot be detected using screened methyl orange. Okay, so over here, this means that I have my acid in the conical flask, so this is my X, and then I'm adding NaOH from the burette. Okay, so over here, NaOH is a strong base. X, I'm not sure whether it's a weak or a strong acid because they didn't say anything about it. So currently, let's just put it like that. Regardless whether it's strong or weak, you'll have roughly this shape. Okay, so this will be y-axis will be pH, and the x-axis will be volume of NaOH added. So over here, this region of rapid pH change, in the middle of it, this is the equivalence point. We talked about this when we were solving the first question, right? So it is a point where your base added exactly neutralizes the amount of acid in the conical flask. Now, over here today, I'd like to introduce a second concept, which is known as endpoint. Endpoint is basically, essentially the pH where indicator changes color. So the endpoint is usually slightly after the equivalence point. Okay, and it is when you have 1 drop of sodium hydroxide added in excess, and only then the indicator will change color. And therefore, you know that it is the end of the titration. And that is how you know that you have reached equivalence point. So usually, when we choose an indicator, we have to choose one whereby the pH where it changes color coincides with this region of rapid pH change. So okay, let's look at screened methyl orange. The working range of screened methyl orange is between 3 to 5, meaning that it will change color between 3 to 5. So over here, if X is a strong acid, then you will have the reaction between a strong acid plus a strong base. So this will give you a neutral salt. So that means that the equivalence point is at pH 7. Okay, and if X equals to the weak acid, then a weak acid reacts with the strong base to give you a basic salt, where it has an equivalent point more than pH 7. Okay, so you can, how do you remember this? You can remember it as between a strong base and a weak acid, the strong base will so-called overpower the weak acid. Hence, the salt will also be basic. That is how you can remember it. However, the actual reasoning is because, for example, let's use ethanoic acid as a weak acid. Okay, so if it reacts with strong base, what does it give me? My basic salt will be CH3COONA plus H2O. Okay, so ethanoic acid is a weak acid, and this salt contains the conjugate base of the weak acid, which is CH3COO-. And this conjugate base undergoes a slight hydrolysis in water to give you the acid plus OH- ions. So this OH- ions, they are responsible for basicity. Therefore, a weak acid and a strong base will react to give you a basic salt. Okay, so hence if you look at this, either in any case, whether it's a strong acid or a weak acid, you will get pH at equivalence point of either 7 or beyond. So hence green metal orange definitely cannot detect the endpoint, no matter which case it is. Okay, then let's take a look. Which of the following is not correct? So let's look at A. The solution acts as a buffer when 12.5 cm³ of NaOH has been added. So to do this, we have to take a look at what is the amount of acid first. So amount of X equals to 25 over 1000 times 0.1. This will give me an answer of 0.0025 moles. This is the amount of acid. So since it's a monobasic acid, 1 mole of acid reacts with 1 mole of base to give you 1 mole of salt. So therefore, it will also need 0.0025 moles of sodium hydroxide to completely neutralize it. So let me write that down. Amount of NaOH required to completely neutralize X is equivalent to 0.0025 mole as well. So let me see, when I have 12.5 cm³ of sodium hydroxide, let me see how many moles do I have. 0.2. So this will give me 0.005 mole. So wow, I have twice of what is required. So therefore, it is already past equivalence point. So beyond the equivalence point, let us take a look. They said that the solution acts as a buffer when 12.5 cm³ of sodium hydroxide has been added. So this is related to question 1 of ionic equilibrium. So over here, if X is a strong acid, then I will have no buffer, because strong acid and strong base, there's nothing weak. If X is a weak acid, then since the weak acid is in the conical flask, it will form a buffer before equivalence point. So this is twice the amount required for exact neutralization. This means that when you add in 12.5 cm³ of NaOH, you have already exceeded the equivalence point. Therefore, this is definitely not correct. Hence, this is the answer. Next, let's look at B. The initial pH of the solution is more than 1. Okay, so over here, well, again, I don't know whether it's a strong or a weak acid. However, I know that if it is a strong acid, then pH equals to negative log concentration of H+. Then this concentration of H+ is equivalent to the concentration of the acid X. Because if it's a strong acid, then it will ionize completely in water to give you H+ ions, correct? So let me just give you an example. So for example, HCl being a strong acid, it will dissociate completely in water to give you H+ and Cl-. So therefore, if there was X mole of HCl, it would dissociate to give you X mole of H+ as well. So this is why if it's a strong acid, negative log H+ would be the same as negative log concentration of X. So in that case, it will be negative log 0.1, which will give you an answer of 1. Okay. So over here, like we said, we are not very sure. So then, okay, I know that this is if it's a strong acid with pH 1. Okay, so they said the initial pH is more than 1. So this is indicating that X is a weak acid. If X is a weak acid, B is true. Let's take a look at C. pH of the equivalence point is more than 7. So again, that's already mentioned. So if it's strong acid, it'll be 7. If it's weak, it'll be more than 7. And D, acid X is a weak acid. So you see, there can only be one answer, which is not correct. So B, C, and D all are all based on the fact that X is a weak acid. So therefore, over here, it cannot have, if X is really a weak acid, then all of these are correct and then only A is wrong. If X is a strong acid, then B, C, and D are wrong, which cannot be possible because you're only supposed to have one more answer. So therefore, it must mean that acid X is a weak acid. So therefore, B, C, and D are all correct. Therefore, they are not the answer. So therefore, the answer is A. Thank you so much for listening and stay tuned for the next question. Thank you.